Right, so good morning, everyone. Uh, let's start today's session. So we are currently now dealing with or studying about the magnetic field. In the last session, we started the magnetic field. Right, so there are basically two types of magnet: permanent and induced magnet. As this, and then we learned about what happens to a conductor kept a current carrying conductor. Right? Current carrying conductor kept kept in a magnetic field, right? Kept in a magnetic field, and eventually we found that it would be shifted. It would be shifted towards some direction, right? It will be thrown away, right? And that is due to the magnetic force acting on that conductor, right? Which is can be found by F is equal bi delta L sine theta. B is called the magnetic flux density, right? Magnetic flux density, and I is called the magnetic flux density, which is the unit is Tesla, and I is the current through the conductor. Delta L is the length of the conductor. Sine theta, the theta value is the angle between the conductor and the magnetic field. Right? So when the angle becomes 90, or when the uh, the direction of current and the direction of magnetic field becomes perpendicular to each other, this magnetic force, right? It becomes the maximum, right? Then we have this VI delta F. And then we looked about some uh, distribution, magnetic field distribution around some type of magnet. For example, a bar magnet, a horseshoe magnet. So you can see here always, unlike in electric field where we had a separate positive charge or a negative charge, that separate positive charge or a negative charge could generate a electric field around it. But here, the difference here is, here there cannot be a sole north pole or south pole, right? North pole or south pole. I mean, its north pole and south pole comes because of the Earth magnetic field, right? Earth is subjected to magnetic field, and that magnetic field start from the north pole towards the south. Right? That's why the starting point of the magnetic field is called as north pole, and uh, the other end is called as the south. That notation is used for other types of magnet as well. Right. Right. So here also you can see there are always the north pole and both north pole and south pole are on the same magnet. Right? They cannot be kept separately, like north pole and there's another south pole magnet. No, they are on the same magnet. Right? Here, uh, magnetic field around current carrying conductor. Right? To find the magnetic field around current carrying conductor, so these are called the induced magnet. Right? These two are permanent magnet, and these are induced magnet. To find the direction of uh, magnetic field, we can use the right hand corkscrew rule. Right hand corkscrew rule. When our forefingers or the thumb is pointed towards the direction of current, the other uh, right, so other section would be pointed towards the direction of the magnetic field. Like here, so our thumb is pointed outward from the board. Then the four fingers would be directed in anti-clockwise manner. Magnetic field is in anti-clockwise manner. Right. Then as here we learned that conductor would be shifted, current carrying conductor would be shifted, kept in a magnetic field to find the direction of this force applied on this current carrying conductor, we can use a Fleming left hand rule to find the force acting on a current carrying conductor, which is kept in a magnetic field. The Fleming left hand rule would be used. Fleming left hand rule. And so Fleming left hand rule states that when there's three fingers, thumb, forefinger, and middle finger is kept perpendicular to each other, right? Is kept perpendicular to each other. And when the forefinger is directed towards the magnetic field and the middle finger towards the current, eventually the thumb would be pointed towards the magnetic direction of the magnetic force, right? First, from that Fleming's left hand rule, we can easily find the direction of the magnetic force applied on a current carrying conductor. Then here we modified the previous equation VI delta L sine theta, which is for a conductor, to here we manipulate that above expression and found an expression for magnetic force acting on a charge, right? Acting on a moving charge in a magnetic field. And there we have VQ V sine theta. VQ V sine theta, where V is the magnetic flux density, Q is the charge of the amount of charge, and V is the velocity, the velocity that the charge is traveling. And so same theta is the direction between the velocity and the angle between the velocity and the magnetic field. Right. So here we could see that when a charge travels in a magnetic field, is perpendicular to the direction of motion, the magnetic force field, the magnetic force is always acting perpendicular to the direction of motion. That is actually perpendicular direction of motion. So the result of that act as a centripetal force. Here the magnetic force acts as a centripetal force. So therefore the result is of circular motion. Right. So here this should have circular motion like this. This particle, the charge, would follow a circular motion. Right. So before moving on to the next section, let's try some additional questions from the previous lecture that we already learned. So here we have a magnet with magnetic flux density 1 Tesla. Between the poles is placed on a electronic balance, a rectangular wire loop of resistance 10 ohm. 10 ohm, which is connected to 40 volt battery with zero internal resistance, is placed in between the poles of the magnet so that the side AB of the loop is completely inside the magnetic field, right? Inside the magnetic field, and the plane of the loop is perpendicular to the magnetic field as shown in the figure. The loop, right? So the loop is firmly fixed to avoid any movement, and this loop is fixed to avoid any movement when the switch SC is closed. The reading of the electric balance, what would happen? The reading of the electric balance. What would happen to the reading of the electric balance? Right, so we have a magnet like this. right? North pole, north south. The one is south. Right, so the magnetic field is in this direction. Conductor AB. Right, so this is the AB conductor. So this is the other side. Right, so the current. This is the loop. So current is flowing in this manner. Then using we can find using the Fleming's left hand rule. So point the forefinger towards the direction of the magnetic field, and this is middle finger towards the current. So force acting on the wire loop is toward downward. Force acting on the wire loop is toward downward, and this is fixed. The wire loop is firmly fixed; it cannot move in. It is not. It is not. It is impossible to move it. Right? It is fixed. Right? It's rigidly fixed. So this is magnetic force acting on the wire loop is downward. And so I think we can find that. Right? Where B is given 1 Tesla. This resistance is also given. Right? Then the wire loop resistance 10 ohm. Right? Here resistance of the wire loop is 10 ohm. 40-volt battery. So here tell resistor is placed between poles of the magnet, so then AB is completely inside the magnetic field. That's a 5 centimeter. Right? It is noted in the figure that this length AB is 5 centimeters. Five centimeters. Yes. That's first we can find the current I. That current I through the loop. Using delta V equal IR on loop. Right? Delta V is equal to 40. I R is 10. So I is 4 amperes. Right? Then we can use F equals VI. V is equal BI L. That BI L. Since the current direction of current is perpendicular to the direction of the magnetic field, sine theta becomes 1. Sine 90. 91. Yeah. 1 into I is 4 into L is 5 into 10 to the power minus 2 meters. That's so which is 2 into 10 to the power 1 Newton. 0.2 Newton. 0.2 Newton, is acting downward downward on the loop, right? So then the same force, right? According to Newton's third law, right? Same force, same action and reaction. Where for any action, there should be reaction force acting in the opposite direction on the other object. So there is a force acting upward, FB, on the magnet. And that is also equal to this value, 0.2 Newton. 0.2 Newton. 0.2 Newton. Right then, uh, right then using F equal mg, right? Okay. Considering the magnet. Now we consider the magnet. Considering magnet. Considering magnet. So they're asking about it happened to the electronic balance. Reading of the electronic balance. Reading of the electronic balance. So what would happen to reading of the electronic balance? Now the magnet is magnetic force is applied on the magnet such that it is dragged upward a bit. So the electronic balance, the reading of the electronic balance should decrease. But by how, what should decrease? Right. So 0.2 Newton is equal to actually delta m g. Delta mg change in uh, change in mass is equal to 0.2 Newton. Right. So then delta m is equal 0.02 kilogram in grams is 20 grams. 20 grams. So the mass, so the reading would be decreased by 20 grams. Decreased by 20 grams. So the answer is second one. Right. Answer is second one. And so due to this magnetic field, due to this magnetic force, Fp acting on the magnet, which is upward direction, the reading of the balance would be decreased by 20 grams. Right, so this question is, say a particle P moves in a uniform field on the plane of the paper as shown in the diagram. Which of the following combination of the type of particle and the field will give rise to the above motion? Right, so you can see here the particle is shifting downward. Right, shifting downward. Yes, shifting downward. Type of particle field. So positive charge and electric field. Right, so could A be true? Right, if it is an electric field acting downward, electric field and a positive charge. So then what would happen? It would be shifted downward. That is correct. Yeah. Electric force would be act downward. So it would go down. So that is first one is correct. It would have this path. B negatively charged magnetic field. Now it is a magnetic field. Acts downward. B negatively charged. Moving here. The negatively charged moving towards right means current is moving towards left. At current towards left. At current towards left, magnetic field is downward. So what is the direction of force? Using left angle, we can find that. Right? So point the forefinger towards down and the middle finger towards left. Towards left. So then they are to produce a magnetic force field, magnetic force outward from the wall, right? So outward from the wall, right? So we then it will not shift downward, right? Magnetic force act outward from the wall on the particle, it would not go downward. So B is incorrect. Uncharged gravitational. Uncharged gravitational. C. Gravitational force acting down, and gravitational force G acts downward and uncharged particle move here. Right, so that is also correct. Right, that is also correct. Mg act downward, so the particle will be shifted downward. C, correct. The answer is A and C. The possible answers, possible combinations. Next question: a charged particle having velocity v. Charged particle having velocity v enters perpendicular to uniform magnetic field of large density b and follows a circular path of radius r as shown in the figure. If the charge on the particle is q, the mass of the particle is. Right. So they are acts. They act the magnetic field in this direction, which would act as a central force. So what can I do is just apply F equal m towards the center, which is FB, is equal the central force. So B can be found B Q V M central force V squared over R. So the mass of the particle is B Q R divided by V. PQR divided by V. First answer. Mass. Let's see easily by applying a equal limit to a center can be solved. Right. Next question: a charged particle moving in a circular path of radius r perpendicular to uniform magnetic field. Let a charged particle moving in a circular path of radius r perpendicular to uniform magnetic field enters through a thin aluminium sheet as shown in the figure. Right? Shown in the figure. If half of the initial kinetic energy lost due to the penetration, what would be the radius of the new particle? So kinetic energy is K before penetrating to the aluminium, before penetrating to the aluminium sheet. After going through the aluminium sheet, kinetic energy reduced by half. So K divided by 2. So they ask you what will be the radius of the path. Radius of the path. Right. So let's find. So we can find initially. That's how to solve this. Let's try to get the expression for K in terms of R. Hmm. The magnetic field is B and mass is simple then of the particle. So charge is also Q. So K is R mv square. Half mv square if the velocity is V, half mv square. Then K over 2 is 1/4 of mv square. 1/4 of mv squared. Then apply F equal ma to a center. F equal ma to a center before penetration. Right? Before penetration, B before penetration. It is B U V is equal M squared over R. Squared over R. And after the penetration, right, so after the penetration, also we can apply towards the center. Equal ma. After the penetration. After the penetration. After the penetration. Let's say velocity is V dash. After the penetration, velocity is V dash. After the temperature is path. Velocity is V dash. Then V remains same, Q remains in V dash. M remains in V dash squared over R dash and different radius. Different radius, radii. And So it is given after the penetration, it becomes half of K, right? So half of K is equal to half M V dash square. Half M V dash square. Then by solving these two equations, right? Solving these two equations, we can find V dash in terms of V using 1 and 2. 1 and 2 V dash squared half V squared. So V dash is equal to V over root 2. Since V is greater than 0, V over root 2. V dash. Then we can substitute for this. So third equation, V cube, V dash. V dash is V over root 2 mv dash squared over r dash. So V squared over 2 over r dash. R dash. And we have this equation 4. Let's say divide these two. Let's divide these two. Let's say this is 3 dash. 4 divided by 3 dash. 4 we have V QV. V root 2 mv squared over r into mv squared over 2r dash. VQV cancel out. M squared over r dash. At r dash we get r over root 2. The new radius, radii, the path is r over root 2. The second answer. Right, so let's try this question. So here it is 4, right? 400 volt per meter. Not that velocity is 400 as 400. Right, so it is here said uniform magnetic field of flux density 1B, 1 Tesla, and uniform electric field of intensity 300 are parallel to each other in region as shown in this figure. Particle charge positive Q enters at a velocity 400 ms minus 1. Perpendicular to the field and perpendicular to the field and directed into the plane of paper. Charge is directed into the plane of paper. The magnitude of the resulting force acting on the particle is. So electric field, right? So here The direction of electric field is direction of electrostatic force is towards right. Right, so it is a positive charge, positive key charge. Electric field is in this direction. Force is positive charge, it's negative charge. And so positive charge will be attracted towards the negative charge, repelled by the positive charge. So this the electric field, electrostatic force is uh, acting in that manner towards right. So what is the direction of magnetic field? Direction of magnetic field. So using Fleming's left hand rule, we can find the direction of magnetic field. Right. So point the forefinger towards the direction of magnetic field towards right. Current. Middle finger towards the direction of the current to the right. Magnetic field is pointed down. FB. Then we can find FB and FB. E is equal EQ. EQ, so is given E as we have Q. If B, PQ, V. V is given 400, V is 1. So 400 Q. Right, the resultant force, to find the resultant force, what you have to do, just guess the Pythagoras theorem. Find the resultant force, F. So for 300 Q squared plus squared, take the whole square. 500 Q. It's the answer. Right. Right. So let's move on to the theory part, which is named as Hall effect. Hall effect. Right. Hall effect. So that is a special phenomena, right? Special incident that is observed in a current carrying conductor. It can be observed in a current carrying conductor, a special incident, right? So that is due to this magnetic field. Right? Magnetic field can be described using this previous knowledge, magnetic left hand rule. So for it was discovered by a scientist called Edwin Hall around 1870. That's why it is called a Hall effect. Hall effect. This special phenomena that occurs that occurs within current carrying conductor that occurs within current carrying conductor is first observed by scientist Edwin Hall in 1879. So that is why it is called Hall effect. It is named as Hall effect. Hall effect, right? Named as Hall effect. Right. So let's consider conductor like this. Right. So we have a conductor. So this is a conductor, and a magnetic field is there in the conductor. Even within the conductor, magnetic field is there into the whiteboard. Right, into the whiteboard, there's a magnetic field going into the whiteboard, and this is a conductor. This is a conductor. Right, so the electron, let's say electron would move towards right. And this is moving towards right. Then using the Fleming left-hand rule, right? So if current flow means it is a flow of electron. So using Fleming left-hand rule, we can find the direction of magnetic force acting on these electrons, and for in the forefinger in the direction of the magnetic field, middle finger towards the current. Right? So force is acting on FB, right? FB. Likewise, on other electrons as well. Right? So there are a bunch of electrons traveling. Current flow is the movement of electrons. Right? So on all of these electrons, a magnetic force will be induced down, pick them down. So what will be the result? Right? So what will be the result then? Now the electrons are shifted downward. Right? So now there are more electrons on the bottom, right? On the bottom of this conductor. Yeah, there are more electrons on the bottom of the conductor. Right? So there are more electrons on the bottom of the conductor. So due to that, uh, now the bottom of the conductor is negatively charged. Right? So we can see the bottom of the conductor is negatively charged. And this above part, and this part is conductor is positively charged now relative to the bottom of the conductor. Electrons are accumulated on the bottom of the conductor due to the force, magnetic force acted on them. They are shifted downward. Now the bottom side is negative charge relative to the top side, right? Top region, right? Then what would happen due to that? Yeah, due to the magnetic force acting, magnetic force acting on electrons they would be shifted downwards, making the bottom part of the conductor creating more negative. More negatively charged relative to the above part, right? Relative to the top part, right? So which should induce an electric field in downward direction. That's so we should. So the result is an electric field, uh, uh, acting downward. Electric field is from positive to negative charge, right? We can redraw the conductor, right? Redraw the conductor. So this magnetic field B, and now this is positively charged. The top layer is positively charged, whereas the bottom layer is negatively charged due to the accumulation of the electrons. So the electric field would be now downward. Electric field would be now downward. Electric field would now be generated downward. Now, when electron move in this manner, right? So the previous force is there, the magnetic force is there acting downward, and then in addition to that, so due to this electric field, electrostatic force also be acted on the electrons in upward direction. Right? Upward direction. Now, the previous magnetic field also there, magnetic force also there acting downward. But in addition to that, now due to this electric field, newly induced electric field, electrostatic force also would be generated in upward direction. In upward direction, but in upward direction. So there comes an instance you can see. So gradually, when more higher number of electrons accumulated on the bottom layer of the conductor, the electric field would increase. And electric field would increase, whereas the electrostatic force also would increase. And there comes a point where you can see that when electrons get accumulated on the bottom layer of the conductor, right, the electric field increases actually. In this charge, right, in this potential difference, it increased, right? Potential difference get increased, right? When this potential difference get increased, uh, potential difference get increased, the electric field increases, right? Electric field is minus dV over dt. It's dV over dx. So when more electrons get accumulated on the bottom layer, the potential difference increases. As a result of the electric field increases. When the electric field increases, electrostatic force also increases. Electrostatic force also increases. And now, due to the induced electric field, now due to the induced electric fields, electrostatic force is generated, electrostatic force generated in upward direction, right? In upward direction, electrostatic force is generated in upward direction, and electrostatic force is generated upward direction. But initially it is peak, right? Because initially the number of electrons on the bottom layer is low. The potential difference is low, electric field is low, then electrostatic force is low. But initially it is weaker, in upward direction, but initially Fp is weaker. P is weaker, is higher than Fp. So more so electrons would be shifted down furthermore. So electrons are shifted downwards. Furthermore, making or increasing the negative charge of the bottom layer. Furthermore, increasing the negative charge of the bottom layer, resulting higher electric field intensity. Bottom layer, right? Which would increase the electric field intensity. Which would increase electric which would increase the electric field intensity as well as electrostatic field. As well as electrostatic force. electrostatic force, Fp. Right, electrostatic force is also increased. Right, electrostatic force is also increased. Then gradually, force gradually, right? And so initially the electrostatic force is weaker, Fp is higher, so electrons would be furthermore shifted downward. Now due to the uh, accumulation of the additional electrons, the electric field intensity would go up, and Fp also would go up. Right, so gradually, so there comes an instant where Fp is equal Fb. Right, so there comes an instance where F is becomes equal Fb, where Fb equals Fv becomes where Fb becomes equal Fv. That Fv, right? Fv. So thereafter, what would happen? Fv. Then the resultant force acting on electrons would be 0. Then resultant force acting on the electron is 0. Electron is 0. So if the resultant force acting on the electron is 0, P become equal to Fp. And so Fp equal Fb. Equal Fb. Then what would happen? The electron would not be shifted, or electron would move in a straight line. Therefore, the electron is shifted, and therefore the electron is shifted. And therefore, the electron is moving in a straight line. Therefore, the electron, therefore, uh, therefore the electron is, therefore the electron is moving in a straight line, not shifted downward. It's not shifted downwards. It would move in a straight line. It moves in a straight line. It moves in a straight line. It moves in a straight line. It would move in a straight line. Move in a straight line. Then thereafter, the voltage would not change actually. So, because no more electrons would be accumulated on the bottom part of the conductor. So, voltage would be remain same, and that is called as a Hall voltage. And so, thereafter, voltage across the conductor. Thereafter, the voltage across the conductor remains. Thereafter, the voltage across the conductor remains same, and it is referred as called as Hall voltage. It is referred as Hall voltage. It is called as a Hall voltage. That's a VH. VH. Right, so we can find actually the VH distance is D. But right, so if this distance is D, and the voltage difference is VH. And so electric field intensity can be written as E is equal a Hall voltage over D, when Hall voltage is as attained, or in other words, when the electron is moving in a straight line, or when steady state. Right. And let's say the velocity is V, drift velocity is V. So drift velocity is Vd. Then we can write if G is equal Q. VH over D is equal Q. VH over D is equal VH over D into Q. If B would be written as B Q Vd, drift velocity. Vd is the drift velocity. Right. So when steady state is attained, under steady state, under steady state, if B is equal to E, and if B is equal to FP, VHQ over D is equal E. D is equal VHQ over D. VH all voltage is equal. Q get cancelled out. D VD all voltage. Right? VD all voltage. Right, so what you have to do is under steady state, the magnetic field, magnetic force become equal to electrostatic force. B is the magnetic flux density. D is the height, right? Height, the distance, height of the conductor, height of the conductor, diameter, can say diameter or height. Length in the length in the direction of electric field. Right? It is the height of the conductor in the direction of electric field. Right? In the direction of electric field, not other height. Right? Conductor in the direction of electric field. VD is the drift velocity. Drift velocity. Right. So this is the basic equation we have. Right. So what we have to remember is under steady state, FB is equal FV. That you can easily you don't have to remember this equation VH is equal to VD into ED. And what we have to do is just remember the condition under steady state, electric field, electrostatic force becomes equal magnetic force. Then easily you can plus up equally this can be derived. Right. So then let's try to get another expression for Hall voltage, some different another expression in terms of I, right? In terms of I, Right. So consider a, conductor, as follows. Conductor consider rectangular conductor as follows. Rectangular shaped conductor. Rectangle shaped conductor as follows. So the magnetic field is let's say acting in this direction. Magnetic field is acting in this direction. current flow in this direction. Current flow in this direction. The magnetic field is at B. Current flow in this direction. Let's say D. The height. T is the width of the conductor. That is the conductor. Conductor, right? So if we consider electron, so current flow is towards right, electron flow is towards the opposite direction. What would be the direction of the electric field? Okay. Yeah, upwards. Electric field would be induced in upward direction. Right, so currently the above expression, we can find VH. VH is VD, VD. V into D, drift velocity. Then from the above knowledge, from the previous knowledge, we found that from so I can be written as current I. Right. From different current electricity. In current electricity, from current electricity, there's the equation for current, which is P T drift velocity into area of the conductor. Area of the conductor parallel to the perpendicular to the direction of current flow. This A into end E. Ne. And N is the number of free electrons in per unit volume. E is the charge. E is the charge. Right? E is the charge, amount of charge of an electron. And then here, subject drift velocity I, A, N, E. A is also can be substituted T into T, N, E. Right? Can use this two equation. Find expression for Hall voltage. At Hall voltage in terms of phi, B to D into VD D get cancelled out. BI T and E. Now the expression for Hall voltage in terms of current. In terms of current. Here also this can be AC derive, right? NBC derive. You don't have to within couple of seconds. What is important here is basic principle. Under steady state, P is equal FP. Then from that basic principle, you can easily derive this equation. So V is the electric flux density, I is current to the conductor. V magnetic flux density. N is the number of free electrons per unit volume. Number of electrons per unit volume. V is the what is the number of electrons per unit volume? V is the electric charge, right? Charge of an electron is 1.5 10 to the power minus 90, minus 1.9 10 to the power 90. An electron, charge of an electron, right? So what is T? T is the T is the height in the direction of magnetic field. Initially, it was D is the height in the conductor in the direction of electric field. Now it is in the magnetic. T is the height in the direction of magnetic field. Height or thickness. The thickness. Thickness of the conductor in the direction of magnetic field. So this is the Hall effect, right? And this equation you don't have to remember. Just easily derive them. It's the basic principle. P is equal FP under steady state. Right. So some application of Hall effect. This Hall effect it can be used to check whether a semiconductor is N-type or P-type. So N-type, and there are two types of semiconductor which you learn on electronics. Right. So to identify whether a semiconductor is N-type or P-type, this Hall effect could be used to determine whether uh, to determine whether a semiconductor is N-type or P-type. To determine whether a semiconductor is N-type or P-type. One application, or another application is to find the electric flux, magnetic flux density. You can find B, right? You can find B, and if Hall voltage is measured and the thickness is known, number of free electrons per unit volume is also known, and the charge of an electron is also known. So I can be measured. Then electric, magnetic to find the magnetic flux density. Find the magnetic flux density, B. Another application is in medicine, right? In medicine, to find the blood flow rate, right? It's called an electromagnetic flow meter. To find the blood flow rate also, this Hall effect is used. Find the blood flow rate of a patient. The instrument called electromagnetic flow meter. Patient. The instrument called electromagnetic uh, instrument called electromagnetic flow meter. Is used, which is well on this Hall effect. Governed by this Hall effect. By this Hall effect. Right, so these are some application of Hall effects. Right, let's go over some examples. Right, so what you have to know is when under steady state, PV is equal electric field, electric force becomes equal to the magnetic force. And the electron will be without, I mean, in a straight line, without shifting either downward or upward. Consider the following statements made regarding the Hall effect. Consider the following statements made regarding the Hall effect. The sign, positive or negative, of the Hall voltage is independent of sign of the current carriers in the Right. So is that true? A. Let's say current is flowing in this direction. So electron. So because the electron flow is in the opposite direction. Magnetic field is in this manner, right? And the electrons would be shifted upward, right? Electrons would be shifted upward. This would be negatively charged. This would be positively charged. All voltage is in this manner. If it is, if the current carriers are electrons, if the current carriers are holes, positive charges, say positive charges, same, we have same magnetic field, same magnetic field, B. Now, current is same. This now this would be shifted upward. Shifted upward, so this would be positively charged. Charge voltage now all voltage is from higher uh, higher potential, low potential, so towards downward. So first one is incorrect. Sign of the voltage is dependent on the sign of the current carriers. It's not independent. A whole voltage is not generated when the direction of the magnetic field is parallel to the direction of the current. Yes, that's true. Whole voltage is not generated when the direction of the magnetic field is parallel to the direction of the current. So when they are parallel, no shifting occurs, right? So electron won't be shifted. No whole voltage are not shifted. What either side electrons are not shifted to either side since to either side since to either side since both current is both current and magnetic. Since both current and magnetic field, current and magnetic field are parallel. Therefore, no pole voltage. No whole voltage. Whole voltage. Correct. Whole becomes consequence of force acting on a moving charge in a magnetic field. The Hall effect is a consequence of force acting on a moving charge in a magnetic field. Yes, that's correct. So B and C. Right? So the Hall effect is Hall effect happens due to the force acting on the moving charge. It's correct. Right, so this is the answer. A and A is incorrect. B and C are correct. A beam of electrons enters the region between two charge parallel plates with speed 10 rate forces ms minus 1 as shown in the figure. The potential difference across the place is 200 volt and the beam along the y direction. Magnetic field, you got to uh, keep the beam along the y direction. Beam of electrons. Electron beams travels with velocity of 10 to the power 6 ms minus 1. 10 to the power 6 ms minus 1. Centimeter voltage difference is 100 volts is ground. So what is the direction of the force acting? That's this positive charge now. Direction of electrostatic force is upward, right? To keep the beam along the y direction, the direction of magnetic force should be down, and they should be equal. To keep the path of the electron in the y direction, there should be a magnetic force to compensate for the electrostatic force. It's downward. Right? So in order to have a magnetic force downward, so you see the flame is left hand, you can determine the direction of the magnetic field. Point the arm towards the force, middle finger towards the current. Then there should be a magnetic field into the white paper. So we can find that value. That says FP equal FB. Is equal V over B into Q V Q send out. This is volt event velocity. So we can 6 10 to the power 4 minus 2 to 10 to the minus 2 into the paper. Tesla into the paper. Also is 1. That next question, plate of copper 10 to the power minus 3 meter thick and 4 10 to the power minus 2 meter wide is placed in a uniform magnetic field of flux density B 0.44 T as shown in the figure with a current of 80 amperes plus generate wall voltage of this much. What is the number of free electrons per unit volume of copper? So that we have an expression which is equal BI TNE. And so VH is equal NE. Or here T is the thickness in the direction of, right? T is the thickness in the direction of magnetic field. The direction of magnetic field. Right. So if you don't remember this equation, that's all right. So you can start from the basic principle where V is equal to FP and come for this expression. They're asking about so T is the thickness. So you have to use so the correct thickness here. Right? Yeah, this thickness is also given 0.10 to the power minus 2 and the height is also given 2 into the power minus 3. So you have to find the correct thickness. Thickness in the direction of magnetic field. So NB I H T B I V H T B is 0.4. I is 80. H 0.10 to the power minus 6. T thickness in the direction of magnetic field 2 10 to the power minus 3. E charge charge of electron 1.5 into 10 to the power minus be minus 90. No? So 90 plus 10. 90. 6 into 10 to the power minus one point 5 into 10 to the power 29. Right? Number of electrons per cubic meters. And so that is the answer. This question. Right, so up to now we have learned the magnetic force. Right? We have learned a couple of equations for magnetic force, F. Magnetic force acts on a conductor placed as a current carrying conductor placed in a magnetic field, as well as acts on a charge moving in a magnetic field. Right? Those two equations. And today, and as well as the distribution of magnetic field closer to some type of magnet, like bar magnet, hose magnet, and current carrying conductor, circular current carrying conductor, and a solenoid. Then to how to determine the direction of the magnetic force acts on a conductor or a charge using Fleming's left-hand rule. But still, right? Then today we learned about the Hall effect, right? Hall effect, which is a consequence, which is a result of the magnetic field, which is the magnetic force acts on a acts on electrons or current carriers, which would induce electric field. Then the both after some time, after the steady state is attained, is P become equal to P, electric force become equal to magnetic force. Then we can use that condition here and come up with some equations for Hall voltage. Hall voltage is the corresponding voltage across the conductor when the steady state is attained. Steady state attained means when the electron or the current carriers moves without shifting towards the other side. Discuss couple of application of Hall effect, but still we have not found an equation, expression for this B, electric flux density. Still we have not found an equation. And so next section is about that. Biot-Savart law is a law, so basic law to find the magnetic field intensity, the magnetic field, magnetic flux density. Right? Right, then we can derive some expressions for magnetic field around the current carrying conductor, as well as magnetic loop, current carrying loop, and solenoid using this Biot-Savart law, which we would discuss in the comment section. Today, on this section. So thank you.